Hello. Today we finish up Chapter 1. We talk about Sections 1.3 and 1.4. We will explore inverse functions, exponential functions, and logarithmic functions. Those kind of go together. And we'll explore a bunch of trig function stuff. All right, let's get to it. So, inverse functions. That's basically when you have two functions and one undoes whatever the other does. Here's an example of two functions that are inverses. So f of x equals 5x, g of x equals x over 5. The first function takes an x and it multiplies by 5. The second takes your x and divides by 5. Imagine there's some number, say 2, sitting there all by itself, enjoying life, not a care in the world. Along comes the f function, and f turns 2 into something else. It turns it into 10. And now 10 is sitting there, and along comes the g. The g function takes that 10, and what happens? 10 over 5 is 2. So the f turned the 2 into the 10, the g turned the 10 into the 2. Whatever the f does to a number, the g is going to undo it. Here's another example. Say f of x is 5x plus 2, g of x is x minus 2 over 5. Let's just try another example. F of 1 equals, see, 5 times 1 is 5, plus 2 is 7. And g of 7, if I plug 7 in there, 7 minus 2 is 5. 5 divided by 5 is 1. Functions are inverses if whatever one function does to a number, the other function undoes it. Another way of saying that is f of g of x equals x for all x in the domain of g. So that x is sitting there, g turns x into something, g turns it into g of x, and then f of that thing takes it back to the original g. So composition f of g of x turns into x, but also I need the reverse composition as well, g of f of x. Now, when functions are inverses, we often put a superscript -1 to indicate that they are inverses of each other. So g is the inverse function of f. Or if you want to put the argument x in there as well, that's okay. So inverse functions have interesting graphs, is that when you graph them both, they look like images of each other over this line y equals x. So the f function, for example, I see f of 3, I don't know, it's about 4.5. f of 3 equals 4.5, and f inverse of 4.5, let's find that on the graph. So there's my 4.5, I go up, and the value is 3. It's this switching of the x's and y's that cause this reflection over the line y equals x. Okay, well, the reason we study inverse functions is because we're about to look at two families of functions that are inverses of each other, exponential functions and logarithmic functions. Those are inverses of each other. So exponential functions are functions where the variable is in the exponent. So something like x squared that is not an exponential function. In order to be exponential, the variable is in the exponent. So these are all examples: 0.5 to the x, 10 to the x, e to the x. Even something like 1.6 times 1.05 raised to all this stuff, and x is in the exponent, so it still counts as an exponential function. Here's an example, this GeoGebra file, that shows what exponential function graphs look like. In this example, I can change some parameters of the function. So in general, my function is f of x equals c times a to the kx plus d, and I can change the c, the a, the k, and the d up above. And when I do that, just kind of take a look at those curves. I mean, here is the classic exponential curve. It goes slow, 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 and then it grows faster and faster and faster and faster and faster. So at some point, it's slow growth, and then it just launches way up. That's typically what you think of as exponential growth. You can have exponential decay, where something decays very quickly and then slows down over time. What else here? Just kind of playing around with some of these numbers. It could go below the x-axis. Oh, there we go. So you can have, oh, whenever I change that, it resets it. Graphs that look like exponential curves that are below the x-axis. So you kind of get a sense of generally what these functions look like. Those are exponential functions. Okay, let's go back. Logarithmic functions are the inverses of exponential functions. And here's the graph. So in green, we have the exponential function, and in red, we have the logarithmic function. Now, here's an example. Log base 2 of x is the inverse of 2 to the x. Whatever, we call this the base of the exponential function. In this case, it's 2. Whatever the base of your exponential function is, that number becomes a subscript under log to show the inverse. So log base 2 of x is the inverse of 2 to the x. So 2 to the 5th equals 32. So kind of reversing things around, log base 2 of blank equals blank. What am I going to put in those numbers? Log base 2 of 32 equals 5. The exponential function takes the 5 and turns it into a 32. The logarithmic function takes the 32 and turns it into a 5. Now, if log doesn't have a subscript, then it's understood to be log base 10. That's the common logarithm. And if you see ln, that's the natural log, and that log is the inverse of e to the x, the natural exponential function. Let's talk about trig functions. So we have our three basic trig functions, sine, cosine, and tangent. Notice the input of a trig function is an angle, and the output of a trig function is a ratio of sides. So the input is an angle, the output is a ratio of sides. So in the picture to the right, there's my angle. So for a triangle with this given angle, the sine is figured out by taking the opposite side divided by the hypotenuse. And the cosine is figured out by taking adjacent over hypotenuse, and the tangent is figured out by taking the opposite over the adjacent. There's a mnemonic that some people use, SOHCAHTOA, that might help you remember these ratios, which ratio is associated with which trig function. Sine is opposite over adjacent, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. These are two triangles you must memorize. They are so common, they come up again and again and again. You just have to know the ratios of their sides. So on the left, here's the 45, 45, 90 triangle. And if the legs have length 1, then the hypotenuse has length square root of 2. So when I see a 45-degree triangle, I think 1, 1, square root of 2. The other common triangle is a 30, 60, 90 triangle. The short leg has length 1, and the hypotenuse has length 2, and the long leg has length square root of 3. The way I remember this is that the 30, 60, 90 triangle is really half of an equilateral triangle. An equilateral triangle has angles 60, 60, 60, and all lengths are the same. So if one length has side 2, then half of that length has side 1, and then you can use the Pythagorean theorem to figure out that the remaining side has length square root of 3. So if you can memorize these two triangles, that will help you figure out 95% of all trig problems. For example, pause the video for a second. Try these few examples here. See if you can figure those out by looking at those triangles, and then start the video again when you're ready to check your work. All right, so here we have it. Sine of 45. I look at one of those angles at 45. I want to take opposite over adjacent. Opposite over hypotenuse. So opposite over hypotenuse, and so my answer is 1 divided by the square root of 2. For the cosine of 30, I find a 30-degree angle. There it is right there. Cosine is adjacent over hypotenuse, so I'll take the side adjacent to the angle divided by the hypotenuse, so that's the square root of 3 divided by 2. For tangent of 30 degrees, I find at 30 degrees, tangent is opposite over adjacent, 1 divided by the square root of 3. That's the solution there. Cotangent is the reciprocal of tangent. Right? Cotangent is the reciprocal of tangent. So here's my 45. I'm going to do adjacent over hypotenuse. That flips it over from the normal tangent, but it's still just 1 over 1. And my last problem, secant. Secant is the reciprocal of cosine, 1 over cosine. So cosine is adjacent over hypotenuse. Secant, I find my 60, and I'm going to do hypotenuse over adjacent. So 2 divided by 1. And that gives me 2. Here's a quick demo of some of these trig ideas. We start off with a unit circle. So the radius is 1, and the angles around the unit circle are broken into radians. The key idea to remember is that half the way around a circle is a radian of pi. That's pi radians. And so half of the half takes me up to the top. That's my pi over 2. If I take the top half of the circle and divide it into thirds, I get pi over 3. In fact, let me just highlight pi over 3. So I get pi over 3, 2 of those pi over 3s, 3 of those pi over 3s, I get a full pi, 4/3 pi, 5/3 pi, and then I come back. You can call this 6/3 pi, using 2 pi, or I just come back to 0 again. If I just focus on the fourths of pi, you can see the top half of the circle is pi, so I divide that into 4 parts, and where I come back is pi over 4. The multiples of pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, which is 3/2 pi, 7 pi over 4, and there we go. And you could also break this down into multiples of pi over 6. We sort of visualize angles as segments on the unit circle where the segment goes from the center to an outer part, and the angle is drawn with this positive x-axis. So here's an angle of pi over 3 radians. That's that angle in there right there. Here's an angle of pi over 2 radians, or it's really just a right angle. If I can make it bigger and bigger, here's an angle of 5 pi over 6 radians, and so on. I can go really far, 4 pi over 3, so that big angle is more than 180 degrees. That angle there is 4 pi over 3 radians. Now, once I have my once I have my ray, then I'm going to draw a right triangle. And I draw this by dropping a straight line to the x-axis. So as I move around, I'm going to make a triangle within this unit circle. And then finally, the final step in all this is to label the signed side lengths. So this angle of pi over 3, this is an angle of pi over 3, that's really the same thing as 60 degrees. So this triangle is a 30, 60, 90 triangle. And so if I label the side lengths, these side lengths are 1, 2, square root of 3. If I drop this down a little bit, there's my 45, 90 triangle. So an angle of pi over 4 radians is the same as 45 degrees. And the side lengths are 1, 1, square root of 2. Here's another 30, 60, 90 triangle, and the side length ratio is 1, 2, square root of 3. Now, look what happens when I move this into a different quadrant. I'm going to take this and push it over here, and look at the side lengths now. And now I have a -1 because this x part of the leg of the triangle is going into negative x territory. So I'm going to call that a -1. And if I go further into the third quadrant, now I also have a negative on the y component of the triangle. The y is going down, so we'll call that a -1 and a -3. The hypotenuse is always positive because it just represents the length from the origin to the circle. And then finally, in the fourth quadrant, we see that the y part of the triangle is negative, but the x part of the triangle is positive. So I like to use this idea in order to help me figure out the values of trig functions. So let's do that in this next applet. Okay, in this applet, we have some random angles that are given to us, and we need to figure out some trig functions of those angles. So let's say tangent of 3 pi over 4. So the first step is to move this to 3 pi over 4. So let's remember the full circle, the half circle is pi, but I only want 3/4 of the pi. So 1/4, 2/4, 3/4. So there's my 3/4 pi. I've got the right angle. Let's check that. Good. The next step is to draw the right triangle. So I draw a triangle coming down. The next step after that is to figure out my signed side lengths. So I'm going to put 1 square root of 2. Oh, but that's actually a -1 down there. And now let's actually compute the tangent of 3 pi over 4. Well, it's opposite over adjacent, so 1 divided by -1. And I always use the angle that's touching the origin, sort of as the angle for my calculation. 1 over -1 is -1. I'll type that in, check. Well done, I've answered one problem in a row correctly. Let's try it again. All right, randomly generate something. How about the sine of pi? So that's kind of interesting. What about the sine of pi? Okay, so there's the angle. Okay, check, that's good. What does the right triangle look like? I've drawn the right triangle, but it's actually sort of a collapsed right triangle. Do you see that? So I have a right triangle that's been collapsed. What are the side lengths going to look like? Well, on top, I have the hypotenuse. That's always going to be 1. But this length for the leg down below is going to be a -1. So when it always reaches its extreme there, I get 1 for the hypotenuse, -1 for the leg, and that 0 on the left is the length of the short leg there. So you can see that length shrinks down to 0. So it's a little bit weird doing this calculation on a collapsed triangle, but it works. What is sine? Sine is opposite over hypotenuse. The opposite is 0 over the hypotenuse of 1. 0 divided by 1 equals 0. Put in 0 and check. That's it. Let's do one more. All right, mix it up, mix it up. See, we already did tangent, we already did sine. Let's get something more interesting. Secant of pi over 3. So let's find the pi over 3 angle. There it is. Let's draw the right triangle. Draw it down. Label the side lengths. Do you see what this is going to be? 1, 2, square root of 3. And now compute secant. So let's see, secant is 1 over cosine. So let's remember, cosine is adjacent over hypotenuse, so I want it the other way around. I want 2 over 1. So 2 over 1 is 2. Am I right? Well done. All right, let's get back to the PowerPoint. Trig identities. There are lots and lots of trig identities out there in the world, but there's only one that you must memorize, and this is it. Sine squared plus cosine squared equals 1. This comes from the Pythagorean theorem. Let's suppose I have a triangle with hypotenuse length 1. Well, it turns out that if I label one of these angles theta, then the adjacent side of this triangle has length cosine theta. That is actually the length of the adjacent side. And the length of the opposite side is sine of theta. So by the Pythagorean theorem, I know that the sine of theta squared, that's the square of one leg, plus cosine of theta squared, that's the length of the other leg, equals 1 squared. And that gives me exactly the identity. Notice that taking a whole sine function and squaring it is the same thing as sine squared of theta. It's just a different way of writing it. Okay. Here's a review, our graphs of trig functions. Remember, sine goes through the origin. It makes somewhat of an S curve as it goes through the origin, and the period is 2 pi. It goes up to a positive 1, down to a negative 1 there. Cosine has a hill above the origin, and again, its period is also 2 pi. Tangent has an interesting graph that it's broken up as a bunch of different pieces. It's not continuous. Oh, and one other thing that's interesting about tangent is that it has a period of pi. See, it goes, let's say we start at 0, and we go up, and it disappears, and we come up from the bottom, and we get to pi, and then it repeats. So this function repeats every pi. So sine and cosine have a period of 2 pi, but tangent has a period of pi. Inverse trig functions. I'll only just touch on this very briefly, and a little bit later in the semester we'll see them again. If I have the sine function, I can't take the sine function and just flip it over the line y equals x. In order to get inverse functions, remember, we can take a graph and flip it over that diagonal. But if I try to flip it over the diagonal, I'll get a picture of something that isn't even a function. It would look like this. It doesn't pass the vertical line test. So the trick with inverse functions is we don't take the entire graph and flip it over. We're only going to take a little segment. That's what's in bold. I take that little segment there and I flip that segment over the line y equals x, and I get the new picture. So this picture on the right, that is the graph of the inverse of sine. That's the entire graph. I'm not leaving anything out of the picture. Sine inverse is just a little squiggle in the middle of the graph and nothing more. Sine of pi over 2 equals 1, and so sine inverse of 1 equals pi over 2. They reverse each other. And sine of pi over 6, you could figure this out with triangles. Sine of pi over 6 is 1/2, and so sine inverse undoes that. Sine inverse of 1/2 equals pi over 6. And that's where I will leave it for chapter 1, and let me know if you have any questions.